candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. The universe. The universe contains many billions of galaxies. There are three types of galaxies as spiral, elliptical and irregular. Galaxies are made up of billions of stars. Our galaxy is called the Milky Way. Our Milky Way is a spiral. There are many planetary systems in the galaxy, with planets orbiting a host star. The Milky Way. The Milky Way is one of galaxies in the universe. Its diameter is approximately 100,000 light-years. Our planetary system is called Solar System, and it is located in an outer spiral arm of Milky Way galaxy. The Sun is one of billions of stars in the Milky Way. Other stars in the Milky Way galaxy are much further away from Earth than the Sun is. Some of these stars also have planets which orbit them. The Solar System. Our solar system consists of our star, the Sun, and everything bound to it by gravity. The Sun lies at the center of the solar system. It is a star that makes up over 99% of the mass of the solar system. The 8 planets in our solar system in ascending order of the distance from the Sun are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. There are 4 rocky and small planets, Mercury, Venus, Earth and Mars, that are nearest to the Sun. These are small and dense, and mainly made of rock and iron. There are 4 gaseous and large planets, Jupiter, Saturn, Uranus and Neptune, that are the furthest from the Sun. These are large, mainly gas, and have no solid surface, although they do have a solid core. The 8 planets travel the Sun in the same direction, and in approximately the same plane. The further a planet is from the Sun, the lower its average surface temperature. This is because the intensity of the Sun's radiation weakens with increasing distance. However, as shown in the table, Venus is an exception. Its average surface temperature is higher than Mercury's even though it is farther from the Sun. This is because Venus has a thick atmosphere rich in greenhouse gases, which trap heat and raise the temperature. There are an unknown number of dwarf planets which orbit the Sun, such as Pluto, Eris, Haumea, Makemake, Ceres and others. There are dozens of moons that orbit the planets as near-circular orbit. Moons are an example of natural satellites. There are artificial satellites, are man-made, and can orbit any object in space. There are millions of asteroids. It is a small rocky object that orbits the Sun. The asteroid belt lies between Mars and Jupiter. There are millions of comets that orbits the Sun as highly eccentric elliptical orbits that extend beyond the planets into the Kuiper belt. Comets are made of dust and ice and orbit the Sun in a different orbit to those of planets. The ice melts when the comet approaches the Sun and forms the comet's tail. There are millions of meteoroids that are rocky fragments of asteroids, comets, moon and planetary collisions. They are much smaller than asteroids, ranging in size from tiny grains up to meters. Further from Neptune, we have discovered Kuiper belt and Oort cloud. Gravitational force. There is a gravitational attractive force between all objects with mass. The gravitational law of Newton states that the attractive force between two masses is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The greater the mass of each object, the stronger the gravitational attraction between them. The closer the objects are, the stronger the gravitational attraction between them. The further apart the objects are, the weaker the gravitational attraction. If the mass of one object is doubled, the forces between them are doubled. However, doubling the mass of both objects together, the forces between them increases fourfold. This is because the force is proportional to the product of their masses. If the distance between two objects is doubled, the forces between them are quartered. This is because the force is inversely proportional to the square of the distance. These forces obey Newton's third law of motion: every action has an equal and opposite reaction. This means that the gravitational forces between two objects are always equal in magnitude and opposite in direction, even though they act on different objects. Gravitational field strength. The gravitational field strength, at a specific point, is the gravitational force exerted per unit mass on an object placed at that point. It is measured in newtons per kilogram. It is a vector quantity, meaning it has both magnitude and direction. The direction is always towards the mass. The gravitational field strength is directly proportional to the mass of the object and inversely proportional to the square of the distance from the object's center of mass. The greater the mass of the object, the stronger its gravitational field. This is why Jupiter, with its massive size, has a much stronger gravitational field than Earth. As shown in the table, a clear relationship exists between the mass of a planet and its gravitational field strength. Heavier planets tend to have stronger gravitational fields. Earth's gravitational field strength is roughly 10 newtons per kilogram, while the Moon's is about 1.6 newtons per kilogram, 6 times weaker. The farther away you are from an object, the weaker its gravitational field. This is why the gravitational field strength decreases as you move further away from a planet's surface. Objects in orbit. With no force acting on any other object in the space, so they will travel through space in a straight line. Gravitational forces exist between all masses, providing the centripetal force that causes planets and other objects to orbit the Sun and moons to orbit planets. Moon and their orbits. Moons are natural satellites that orbit planets because they are closer to their planets than the Sun, experiencing a stronger gravitational pull. These orbits are often not perfectly circular, but they are generally elliptical with the planet at the center. Therefore, the orbit of moons are approximately circular, with the planets at the center. Planets and their orbits. The Sun contains most of the solar system's mass, causing its gravity to pull planets, comets, and asteroids into orbits around it. The Sun's gravitational field strength decreases with distance from the Sun. This causes the orbital speed of planets to decrease farther from the Sun, because the weaker gravitational attraction results in a lower centripetal force, requiring less speed to maintain the orbit. This also leads to longer orbital duration. These orbits are often not perfectly circular, but they are generally elliptical with the planet at the center. Therefore, the orbit of planets are approximately circular, with the Sun is at the center. Comets and their orbit. Comets have highly elliptical orbits, meaning they are elongated compared to planets that is nearly circular orbits. As a comet moves further from the Sun, its speed decreases due to the weakening gravitational pull. At this point, some of its kinetic energy converts into potential energy. As the comet approaches the Sun, the gravitational pull increases, causing the comet to speed up as it gains translational kinetic energy. This happens because some of its potential energy converts back into kinetic energy. The ice melts when the comet approaches the Sun and forms the comet's tail. The comet's tail is always directed away from Sun. At here, comet moves fastest, longest tail and most easily seen. At here, comet moves slowest, shortest tail. Orbital speed. When planets or moons orbit another object, their paths are often nearly circular. In one orbit, the object travels a distance equal to the circumference of its orbit. This distance is equal to 2 pi r, where r is the average radius of the orbit. Time is the one period is the time that it takes to complete one orbit. Therefore, the average orbital speed can be calculated by dividing the total distance traveled in one orbit by the orbital period. This relationship is expressed by the equation v equals 2 pi r over t, where v equals average orbital speed in meters per second. R equals average radius of the orbit in meters. T equals orbital period in seconds. The orbital period is the time it takes for the object to complete one full orbit. The orbital radius is always measured from the center of the object being orbited to the object doing the orbiting. For example, calculate the speed of a satellite that is orbiting 200 kilometers above the Earth's surface and complete one orbit in 1 hour 24 minutes. The radius of the Earth is 6,400 kilometers. The radius of the orbit is measured from the center of the Earth, so the radius of the Earth plus the height of the orbit above the Earth's surface. Radius of orbit equals 200 plus 6,400 is equal to 6,600 kilometers, or equals 6,600,000 meters. Orbital period equals 60 minutes plus 24 minutes times 60 seconds equals 5,040 seconds. Orbital speed equals 2 pi r over t. To substitute, r equals 6,600,000. T equals 5,040. Its result is 8,200 meters per second. Astronomical distance. Stars are so far apart that astronomers use special units to measure their distances. An astronomical unit, AU, is the average distance between the Earth and the Sun. It is approximately 1.5 times 10 to the power of 8 kilometers. Light year, 1 light year, is the distance that light travels in 1 year. It is approximately 9.5 times 10 to the power of 12 kilometers. The speed of light is approximately 300,000 kilometers per second. 1 year has 365 days. 1 day has 24 hours. 1 hour has 60 minutes. And 1 minute has 60 seconds. Using the formula distance equals speed multiply by the time. 1 light year equals 300,000 times 365 times 24 times 60 is equal to 9.5 times 10 to the power of 12 kilometers. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. The stars. Stars exist in a wide range of sizes and colors, from yellow stars like our Sun to red dwarfs and from blue giants to red supergiants. Color classification is used for stars, as the color they emit is related to their surface temperature. Red stars are the coolest, with temperatures around 3,000 Kelvin. While blue stars are the hottest, with temperatures reaching around 30,000 Kelvin. Our Sun is a medium-sized star composed primarily of hydrogen and helium. It radiates most of its energy in the infrared, visible and ultraviolet regions of the electromagnetic spectrum. Nuclear fusion in a star. In the center of a stable star, where immense pressure and temperature exist, hydrogen nuclei fuse to form helium. This nuclear fusion reaction can be represented by the following equation. Deuterium and tritium, both isotopes of hydrogen, can be fused to form a helium nucleus and a neutron. A huge amount of energy is released in this reaction. This energy exerts a pressure that prevents the star from collapsing under its own gravity. Stellar evolution. A star is formed by the interstellar clouds of hydrogen gas and dust called a nebula. A protostar is an interstellar cloud collapsing, causing an increase in temperature as a result of its internal gravitational attraction. Nuclear fusion reactions occur within the core of a protostar. Hydrogen nuclei fuse to form helium nuclei, releasing heat energy and light energy, which keeps the core hot. A protostar becomes a stable star when the inward force of gravitational attraction is balanced by an outward force caused by the high temperature in the core of the star. This stable star is main sequence star. Most less massive stars expand to form red giants, and more massive stars expand to form red supergiants, when most of the hydrogen in the core of the star has been converted to helium. A red giant from a less massive star forms a planetary nebula with a white dwarf star at its core. A red supergiant from a more massive star explodes as a supernova, forming a nebula containing hydrogen and new heavier elements, leaving behind a neutron star, or a black hole at its center. The nebula from a supernova may form new with orbiting planets. The brightness of stars. Astronomers measure the brightness of stars at a standard distance using the absolute magnitude scale. This is because a really bright star far away will look the same as a dim star nearby, so it is difficult to measure the brightness directly. The absolute magnitude scale, as shown in a diagram. The absolute magnitude of stars is a measure of how bright they would be if they were all the same distance away from Earth. This scale runs back to front. The brighter the star, the smaller the magnitude, and the dimmer the star, the larger the magnitude. The brightness of a star depends on two main factors: how much light the star emits, how far away the star is. This is because more distant stars are usually fainter than nearby stars. The Hertzsprung-Russell diagram. Stars are classified using the Hertzsprung-Russell diagram, which is a plot of stars, showing luminosity, or absolute magnitude, on the y-axis, and temperature, or spectral class, on the x-axis. The main features of the Hertzsprung-Russell diagram are: most stars lie on the main sequence. This is the band of stars going from top left to bottom right. Below the main sequence, and slightly to the left, are the white dwarfs. Above the main sequence on the right-hand side are the red giants. Above those are the red supergiants. This means the white dwarfs are dimmer and hotter than the red giants, which are brighter and cooler. Remember, this will still go from dimmest, highest number, at the bottom to brightest, lowest number at the top. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Doppler effect. When a stationary ambulance car emits sound waves, the wave fronts spread out symmetrically, forming circles around the source. If the wave source moves, the waves can become compressed in front of it and stretched behind it. This movement changes the wavelength and frequency of the waves. In front of the source, the wavelength decreases and the frequency increases. Behind the source, the wavelength increases and the frequency decreases. This effect is known as the Doppler effect. The Doppler effect also affects light. If an object moves away from an observer, the wavelength of light it emits increases. This is known as a redshift, because the light appears to shift towards the red end of the electromagnetic spectrum. Redshift. Redshift is an increase in the observed wavelength of electromagnetic radiation emitted from receding stars and galaxies. This means that the light reaching us from these galaxies has its wavelength stretched, shifting it towards the red end of the electromagnetic spectrum compared to the light we observe on Earth. This figure shows the spectra from 5 different objects. The first shows the electromagnetic spectrum from our Sun, or stationary source in laboratory. The second shows the electromagnetic spectrum from a nearby star. Here we can clearly see that the positions of the dark lines have moved towards the red part of the spectrum. The third shows the electromagnetic spectrum from a nearby galaxy. The lines have moved even further towards the red. The fourth is the spectrum from a distant galaxy. The lines have moved even further towards the red. The last spectrum shows the greatest shift for the furthest galaxy. By measuring the amount of redshift in the light from distant galaxies, astronomers can estimate their recession velocity and determine that the universe is indeed expanding. Therefore, the speed at which a galaxy is moving away from the Earth can be found from the change in wavelength of the galaxy's starlight due to redshift. This equation shows us how to calculate the speed at which a star or galaxy is moving relative to us, where lambda 0 is the reference wavelength that measure from sun or stationary source in laboratory. Lambda is the wavelength that measure from the distant galaxies or stars. So, lambda minus lambda 0 is the change in wavelength. V is the velocity of a galaxy. C is the speed of light in vacuum, which is 3 times 10 to the power of 8 meters per second. Redshift supports the Big Bang theory, which proposes that the universe originated from a very hot, dense state and has been expanding ever since. Cosmic microwave background. The discovery of the cosmic microwave background radiation led to the Big Bang theory becoming the currently accepted model. The cosmic microwave background radiation was produced shortly after the universe was formed, and that this radiation has been expanded into the microwave region of electromagnetic spectrum as the universe expanded. The microwave radiation is observed at all points in space around us. The cosmic microwave background radiation is represented by the following map. The cosmic microwave background radiation map with areas of higher and lower temperature. Blue area represents the lower temperature. Orange-red area represents the higher temperature. Places with higher temperature have a higher concentration of galaxies, suns and planets. Places with cooler temperatures have a lower density of galaxies and stars. The Big Bang theory. According to this theory, the universe began about 14 billion years ago when a single, hot superatom erupted in burst of energy called the Big Bang. All the matter in the universe came from this. Here are 2 evidence to support the theory. All distant galaxies show a redshift, and so they are all moving away from us. This implies that the universe as a whole is expanding. Radio telescopes have picked up cosmic background microwave radiation from every direction in space. This may be the heavily redshifted remnants of radiation from the Big Bang. The Big Bang was not an explosion into existing space. Space itself started to expand. The galaxies are separating because the space between them is increasing. To think about this, it helps to use a simplified model of an expanding universe, such as the shown on diagram. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.